In 2024, a team of physicists published a peer-reviewed paper in one of the most respected journals in gravitational physics, demonstrating for the first time a warp drive solution that satisfies every known energy condition using only positive energy, no exotic matter, no negative mass, no violations of known physics. The headlines exploded, but buried in the details was a single word that changes everything: subluminal. The drive does not break the speed of light. Yet somehow, this result has reignited a 30-year chain reaction of serious scientific research into whether the geometry of spacetime itself might be bent, stretched, or reshaped to carry a spacecraft across the stars. The answer is not what you expect. It is far stranger and far more unsettling. If you enjoy deep dives into the science that sits right on the edge between what is real and what might be possible, do me a favor and tap that like button and subscribe. It genuinely helps this channel reach more curious minds. Now, settle in. Get yourself comfortable. Let's begin. Before we travel back to where this all started, we need to address the thing that brought you here: the recent headlines. The breathless articles claiming scientists may have cracked faster than light travel. Something real did happen, and it happened in the pages of one of the most demanding physics journals on the planet. But what actually happened is both less dramatic and more fascinating than the headlines suggest. In May of 2024, a paper appeared in the journal Classical and Quantum Gravity. The authors were Jared Fuchs, Christopher Helmerich, Alexei Bobrick, and several colleagues working through the University of Alabama in Huntsville and a New York-based research organization called Applied Physics. The paper presented a numerical solution for a warp drive, a configuration of spacetime that produces what physicists call a warp effect, where passengers are carried along by the curvature of space itself, rather than being pushed through it by a conventional engine. And here is what made it genuinely significant. The solution satisfied every single one of the classical energy conditions: the weak energy condition, the strong energy condition, the dominant energy condition, the null energy condition, all of them. No exotic matter, no negative energy, no violations of any known physical law. The matter powering this warp drive was regular positive energy matter of the kind that actually exists in our universe. That is a real achievement. Previous warp drive concepts stretching back 30 years had always required something unphysical, some form of matter or energy that has never been observed and may not exist. This paper eliminated that requirement entirely. Fuchs himself described it plainly. Their approach was to avoid needing exotic matter by adding positive energy to the solution, while keeping as much of the warp effect as possible. The result was a thick shell of ordinary, extremely dense matter that creates gravity strong enough to produce a genuine warp bubble, a region of warped space-time that carries its contents forward without any acceleration forces on the passengers inside. But there is a word in that paper that the headlines almost universally buried: subluminal. The warp drive Fuchs and his team described moves slower than the speed of light. It is not a faster-than-light engine. It does not break the cosmic speed limit. It demonstrates that warp-like spacetime effects can be generated within known physics, which is a meaningful advance, but it does not deliver the thing the headlines promised. It does not send anyone to the stars at superluminal speed. Then, in December of 2025, another paper landed in the same journal. This time, the lead author was Harold White, a former NASA engineer who had spent years working on warp concepts at the Johnson Space Center. White and his colleagues at a private research company called Casimir proposed a dramatic reimagining of the warp bubble's geometry. Instead of the smooth, continuous ring of energy in the original warp drive concept, they split the energy into discrete cylindrical structures arranged around the bubble, modular engine-like pods they called nacelles. The design was striking. It looked remarkably like the fictional starship Enterprise from Star Trek, and that resemblance was not accidental. White himself noted that the convergence between theoretical warp geometry and science fiction spacecraft design might reflect something deeper about the physics. The paper was rigorous. It was published in a top journal. It demonstrated that nacelle-based warp geometries are fully consistent with general relativity and offer advantages in engineering flexibility over the original design. But here is what that paper did not do. It did not eliminate the need for exotic energy. White's nacelle design still requires negative energy density, a substance that has never been produced in any laboratory in anything close to the quantities needed. The nacelles are a better architecture for distributing that exotic energy, but the exotic energy is still required. So here is the honest summary. Recent peer-reviewed research has shown that subluminal warp effects can be produced with positive energy alone, and that warp bubble geometries can be redesigned into modular, engineering-friendly configurations. These are genuine advances published in serious journals by credible scientists. But no one has demonstrated a superluminal warp drive that satisfies the energy conditions. No one has eliminated the need for exotic matter at faster than light speeds. No one has built or tested any physical device. The gap between the mathematics and a working starship remains, by any reasonable measure, astronomical. And yet, the field is not dead. It is, by several measures, more active now than at any point in its history. New papers continue to appear. Computational tools have been developed specifically to evaluate warp geometries. Classification systems have been built. The question that should have been closed decades ago keeps generating new results. To understand why, and to understand what it really means, we need to go back to the beginning. Not the beginning of warp drive research, the beginning of the speed limit itself. But before we confront the physics, we need to confront the reason any of this matters. We need to understand why faster-than-light travel is not merely a curiosity for theoretical physicists, but one of the deepest longings in human civilization. Because the desire to break the speed of light is not really about speed, it is about survival. It is about loneliness. Generation. It is about the slowly dawning recognition that the universe may have built walls around every intelligent species that ever existed. Walls made not of stone or steel, but of distance so vast that even light, the fastest thing in nature, takes years to cross the gaps between neighbouring stars. Consider where we are. Earth orbits an ordinary yellow dwarf star in the outer reaches of an ordinary spiral galaxy. The nearest star system, Alpha Centauri, lies 4.4 light-years away. The light you see from it tonight has been travelling at 670 million miles per hour for more than 4 years, and it only just arrived. If you could board a spacecraft travelling at 1% of the speed of light, a velocity more than 15 times faster than any human-made object has ever achieved, the journey would take 440 years. You would not arrive. Your distant descendants might. And Alpha Centauri is the closest star. The galaxy contains somewhere between 200 billion and 400 billion other stars. Many of those stars host planets. Data from the Kepler Space Telescope suggests that roughly 1 in 5 Sun-like stars harbours a rocky planet in the habitable zone, the region where liquid water could exist on the surface. That means our galaxy alone may contain billions of worlds where the conditions for life as we know it are met, billions of potential harbours, billions of possible civilizations, billions of answers to the question that has haunted humanity since we first looked up at the night sky and wondered whether anyone was looking back. But every single one of those worlds is sealed behind the same wall. The distances between stars are not merely large, they are hostile to any form of travel that obeys the known laws of physics. The Milky Way stretches roughly 100,000 light-years from edge to edge. At 1% of light speed, crossing it would take 10 million years. The Andromeda Galaxy lies 2.5 million light-years away. At the same speed, the journey would take 250 million years. Before you arrived, continents on Earth would have rearranged themselves beyond recognition, and the species that launched the mission would almost certainly have gone extinct. These numbers are not obstacles to be overcome with better rockets. They are prison bars built into the geometry of the cosmos. The speed of light transforms the universe from an infinite frontier into a collection of isolated islands, each one separated from its neighbors by gulfs so wide that meaningful contact between them may be fundamentally impossible. If the speed of light is truly the absolute limit on how fast anything can travel, then every civilization that has ever existed or ever will exist is confined to its own tiny corner of the cosmos, unable to reach, communicate with, or even confirm the existence of its nearest neighbors on any timescale relevant to biological life. This is the real reason faster-than-light travel grips the human imagination with such ferocity. It is not about adventure or exploration, though those matter. It is about whether the universe is a home or a prison. It is about whether the hundreds of billions of potentially habitable worlds scattered through our galaxy are neighbors we might one day visit, or lights we can only watch from across an uncrossable void. It is about whether intelligent life is inherently isolated, sealed inside pockets of reachable space that amount to a few dozen star systems at most, or whether the cosmos permits connection across its full magnificent extent. The speed of light does not merely limit how fast we can travel. It determines whether the universe is fundamentally open or fundamentally closed to the civilizations it creates. That is the weight behind every warp drive paper. That is the emotional charge that draws serious physicists to a question they know might have no useful answer. The speed limit is not just a number. It is a verdict on the cosmic prospects of every species that ever develops the intelligence to ask the question. And the question those physicists keep asking, the question that drives the research we are about to explore, is whether that verdict is truly final. Nothing in the universe moves faster than light. This is not a guess. It is not an approximation. It is one of the most precisely confirmed facts in all of physics. Light travels through vacuum at exactly 299,792,458 meters per second. This number is not just a speed. It is a structural constant woven into the fabric of reality itself. It sets the exchange rate between space and time. It determines how mass relates to energy. It dictates the maximum speed at which any cause can produce any effect anywhere in the cosmos. Everything in modern physics, from the behavior of electrons to the expansion of the universe, is built on this single number. The reason no massive object can reach this speed is not that we lack powerful enough engines. It is deeper than engineering. It is baked into the geometry of space-time. In 1905, Albert Einstein published his theory of special relativity, and one of its core predictions was that mass and velocity are not independent quantities. As an object with mass accelerates, its effective inertia increases. The faster it goes, the harder it becomes to accelerate further. This is not a gradual effect that plateaus, it is an asymptotic wall. As an object approaches the speed of light, the energy required to accelerate it further approaches infinity. Not a large number, not an impractically large number. Infinity. You could harness the entire energy output of every star in the observable universe, channel it into a single particle, and that particle would still not reach the speed of light. It would get extraordinarily close. Particle accelerators routinely push protons to 99.9999% of light speed, but that last infinitesimal fraction is forever out of reach. The speed of light is not a barrier you can break with enough force. It is a boundary condition of the universe itself. This has consequences that go beyond transportation. The speed of light is also the speed of causality. It is the fastest rate at which information of any kind can travel from one point in space to another. If you flip a switch on Earth, the earliest moment that event can affect anything on the Moon is 1.3 seconds later, because that is how long light takes to cross the distance. No signal, no force, no influence of any kind can arrive sooner. This is not a technological limitation. It is a law of nature as fundamental as the conservation of energy. Time itself bends to enforce this limit. One of the most counterintuitive predictions of special relativity is time dilation. As an object moves faster, time passes more slowly for that object relative to a stationary observer. At ordinary speeds, the effect is negligible. A passenger on an airplane experiences time less than 0.001% slower than someone on the ground. But at velocities approaching light speed, the effect becomes dramatic. At 90% of light speed, time passes at roughly 44% of the normal rate. At 99%, about 14%. At 99.999%, below 5%. As you approach the speed of light itself, time dilation increases without limit. At exactly the speed of light, time would stop entirely. A photon, from its own perspective, experiences no passage of time at all. It is emitted and absorbed in the same instant, regardless of whether it travelled across a room or across the observable universe. This is not metaphor. It is confirmed experimental fact. Scientists measure time dilation every day using particle accelerators and precision atomic clocks. Muons, created by cosmic rays in Earth's upper atmosphere, survive long enough to reach the surface only because their high velocity causes time to pass more slowly for them relative to the ground. GPS satellites must correct for time dilation to maintain accuracy. The effect is real, measured, and incorporated into working technology. Length contraction accompanies time dilation. As an object approaches the speed of light, distances along the direction of travel compress from the traveler's perspective. Space itself appears to shorten ahead of you. At the speed of light, the distance between any 2 points along the direction of motion would contract to zero. The geometry of space-time conspires from every angle to make the speed of light an impassable threshold. For decades after Einstein, the speed limit appeared to be the end of the conversation. If no object with mass can reach or exceed the speed of light by accelerating through space, then interstellar travel at superluminal speeds is impossible. Even Alpha Centauri, the nearest star at 4.4 light-years, would require 44 years to reach at 10% of the speed of light, a velocity far beyond anything current technology can achieve. The center of our galaxy is 26,000 light-years distant. Even at light speed, you could not reach it in a human lifetime. The observable universe stretches 93 billion light-years across. The distances are so vast that even light, the fastest thing in existence, has not had time to cross from one side to the other since the universe began. Given these numbers, interstellar travel should have been filed away as a beautiful impossibility, and for most practical purposes, it was. But a small number of physicists noticed something peculiar about the speed limit. The ban applies to objects moving through space. It says nothing about space itself. This distinction sounds like wordplay. It is not. It is one of the most important subtleties in all of physics, and it emerges directly from Einstein's other great theory, general relativity, published in 1915, 10 years after special relativity. Where special relativity describes a fixed, rigid space-time that serves as an unchanging stage for physics, general relativity reveals something far more radical. Space-time is not a stage. It is a participant. Mass and energy do not simply exist within space-time. They shape it, they curve it, they stretch and compress and twist it. The geometry of space-time is not fixed at the beginning and left alone. It is dynamic, responsive, and evolving. This is not an abstract mathematical curiosity. You experience curved space-time every second of your life. Gravity, the force that holds you to the floor and keeps the Earth in orbit around the Sun, is not actually a force at all in the Einsteinian sense. It is geometry. The Earth curves the space-time around it, and objects follow the straightest possible paths through that curved geometry, paths that look like acceleration toward the planet, but are actually the natural motion of free-falling objects through warped space. You feel gravity because the floor is preventing you from following your natural path through curved space-time. The floor is pushing you, not the Earth pulling you. This insight, confirmed by over a century of precision experiments, transformed our understanding of mass, motion, and the structure of the cosmos. The evidence for space-time curvature is not subtle. It shows up in instruments we use every day. The Global Positioning System relies on a constellation of satellites orbiting Earth, each carrying a precision atomic clock. Those clocks tick faster than identical clocks on the ground because they experience weaker gravitational curvature at orbital altitude. The gravitational effect alone shifts their timekeeping by roughly 45 microseconds per day. A competing effect from special relativity, caused by the satellite's orbital velocity, pushes roughly 7 microseconds per day in the opposite direction. The net correction is approximately 38 microseconds daily, and if it were not applied, GPS positions would drift by more than 10 kilometers every day. Every time your phone tells you where you are, it is silently correcting for the curvature of space-time that Einstein predicted in 1915. The theory is not abstract. It is running in your pocket. Gravitational lensing provides even more dramatic evidence. When light from a distant galaxy passes near a massive object like a galaxy cluster, the curvature of space-time bends the light's path, distorting and magnifying the distant source. Astronomers have photographed thousands of these gravitational lenses, including spectacular cases where a single background galaxy is smeared into arcs and rings by the foreground mass. The amount of bending reveals the total mass of the lensing object, including dark matter that emits no light. Space-time curvature is not a theoretical convenience. It is a tool astronomers use daily to weigh the invisible contents of the universe. Frame dragging, predicted by general relativity and confirmed by the Gravity Probe B satellite in 2011, shows that a rotating massive object does not merely curve the space-time around it. It drags space-time along with it, like a spinning ball embedded in thick honey. The Earth's rotation creates a tiny but measurable twist in local geometry, roughly 40 milliarcseconds per year, that causes orbiting gyroscopes to precess. The measured value agreed with Einstein's prediction to within approximately 5%, and was later confirmed with greater precision using laser ranging data. Space-time does not merely bend in response to mass. It flows in response to motion. It is a dynamic, responsive medium that participates actively in the physics of the universe. And then there are gravitational waves. In September of 2015, the LIGO detector registered a signal that had traveled 1.3 billion light-years across the cosmos. Two black holes, one 36 times the mass of the Sun and one 29 times, had spiraled together and merged. In the final fraction of a second before collision, they were orbiting each other at more than half the speed of light, and the violence of their merger sent ripples through the fabric of space-time itself. Those ripples, stretching and compressing space by a fraction of the diameter of a proton, crossed a billion light-years of intergalactic void and squeezed the 4-kilometer arms of the LIGO interferometer by less than 1/100th the diameter of a single proton. The signal matched the predictions of general relativity with extraordinary precision. Space-time is not merely curved by mass. It can ripple, oscillate, and carry energy across the universe in waves that travel at exactly the speed of light. These are not exotic or speculative phenomena. They are confirmed, measured, and incorporated into working scientific infrastructure. They establish beyond any reasonable doubt that space-time is a physical thing, a medium with properties, dynamics, and behaviors that respond to mass and energy in precise and predictable ways. And once you accept that space-time is physical, that it bends and flows and ripples and drags, a dangerous question becomes almost impossible to avoid. If space-time can do all of these things naturally, in response to the mass and energy that happens to be present, could it ever be made to do them deliberately? Could the curvature be engineered? Could the flow be directed? Could the ripples be shaped? General relativity describes space-time curvature through a set of equations called the Einstein field equations. These equations relate the distribution of mass and energy in a region to the geometric curvature of that region. They are extraordinarily powerful. These confirmed phenomena, the time corrections in satellite clocks, the bending of distant light by massive objects, the dragging of space by planetary rotation, the ripples from colliding black holes, are not isolated curiosities. They are predictions of a single set of equations. The Einstein field equations also predict the bending of starlight by our own sun, confirmed during the solar eclipse of 1919. They predict the existence of black holes, confirmed by decades of X-ray astronomy, and spectacularly by the direct imaging of a black hole shadow by the Event Horizon Telescope in 2019. Every major prediction of general relativity has been verified. It is one of the most successful theories in the history of science. But general relativity contains something unexpected, something that even Einstein found troubling. The theory does not merely allow space-time to curve gently around stars and planets. It allows space-time to do extraordinary things, to stretch without limit, to fold, to create regions from which nothing can escape, to connect distant points through geometric shortcuts, and in certain configurations, to expand or contract faster than the speed of light. That last statement requires immediate clarification. When physicists say space-time can expand faster than light, they are not violating special relativity. Special relativity prohibits objects from moving through space faster than light. But space-time itself has no speed limit. The expansion of space is not motion in the ordinary sense. It is a change in the metric, the mathematical description of distances between points. When the universe expands, galaxies are not flying away from each other through space like bullets from a gun. The space between them is growing. New distance is being created. And this creation of new distance has no upper bound on its rate. This is confirmed observation, not speculation. The universe is expanding, and it has been expanding since the Big Bang 13.8 billion years ago. Galaxies at the edge of the observable universe are currently receding from us at speeds exceeding 3 times the speed of light. They are not violating any law of physics because they are not moving through space at those speeds. Space is carrying them. The metric is changing. The distance between us and them is growing faster than light can cross it. This is why those galaxies will eventually disappear beyond our cosmic horizon, carried away by expansion that outpaces the fastest possible signal. During the first fraction of a second after the Big Bang, a period called cosmic inflation, the expansion rate was even more extreme. Space doubled in size roughly every 10 to the negative 37 seconds, inflating a region smaller than a proton to a volume larger than the observable universe in a time interval shorter than any physical process can measure. This was not objects moving. This was space itself stretching at rates that make the speed of light look like a rounding error. Here is where the story takes its turn. A small number of physicists looked at this behavior and asked a dangerous question. If space can expand faster than light on cosmic scales, driven by the energy content of the vacuum, could a similar effect ever be produced locally? Could you, in principle, engineer a region of space-time that contracts ahead of you and expands behind you, creating a wave of geometry that carries a spacecraft along without any local violation of the speed limit? The ship would not move through space at all, at least not in any ordinary sense. Space would move the ship. The cosmic speed limit applies to objects traveling through space-time. It says nothing about the rate at which space-time itself can change shape. The geometry that carries galaxies apart at superluminal recession velocities during cosmic expansion is the same geometry, governed by the same equations, as the geometry that might, in principle, carry a spacecraft. This was not science fiction thinking. It was a question posed within the rigorous mathematical framework of general relativity, and the answer turned out to be unsettling. The equations did not say no. They did not produce a contradiction. They did not spit out an inconsistency. Instead, they produced a solution, a valid, self-consistent solution to Einstein's field equations describing exactly the kind of space-time geometry these physicists were imagining. A bubble of flat space, perfectly habitable, surrounded by a region of carefully shaped curvature, moving through the universe at any velocity, including velocities greater than the speed of light, without any object inside the bubble ever locally exceeding light speed. The solution was published in 1994. The physicist who found it was a young Mexican theorist named Miguel Alcubierre, working on his doctorate at Cardiff University in the early 1990s. He expected to prove the concept impossible. Instead, he found a metric, a valid space-time geometry, a mathematical blueprint for exactly the kind of faster-than-light transport that physics was supposed to forbid. But Alcubierre knew, even as he wrote the equations, that his solution came with devastating problems. The paper landed in classical and quantum gravity, carrying the weight of institutional credibility that most speculative ideas never achieve. The mathematics was clean, the logic was sound, the solution was self-consistent within Einstein's framework. If this geometry could be realized physically, it would mean the structure of space-time contains a loophole, one that does not violate the speed limit so much as sidestep it entirely by redefining what movement means. But the geometry required a form of energy that no experiment had ever produced. The amount of that energy was not merely large, it was larger than anything in the known universe. And the geometry raised questions about causality, the ordered relationship between cause and effect, that threatened to undermine the logical consistency of physics itself. What happened next would define 3 decades of theoretical research. Instead of dismissing the result and moving on, physicists kept coming back. They modified the geometry. They recalculated the energy. They looked for loopholes within the loophole. They found new problems and proposed new solutions. They built computational tools to explore families of warp spacetimes that Alcubierre had never imagined. The pattern repeated itself again and again. A breakthrough would appear. Excitement would build. Then a devastating limitation would emerge. And just when the field seemed dead, someone would find another narrow crack in the wall. That pattern continues to this day. It is the reason those recent papers exist. It is the reason credible scientists at credible institutions continue to publish incredible journals about a topic that sounds like it belongs in fiction. The warp drive did not become real, but it refused to become impossible. And the story of how that happened, of how the most forbidden idea in physics kept finding just enough theoretical oxygen to survive, begins not with warp drives at all, but with an even stranger idea that came first. The idea of reshaping space-time to create shortcuts did not begin with warp drives. It began with wormholes. And the story of how physicists came to take wormholes seriously is essential to understanding why the Alcubierre drive was not dismissed as fantasy when it appeared 6 years later. The concept traces back to Einstein himself. In 1935, Einstein and his collaborator Nathan Rosen published a paper examining the mathematical structure of what we now call black holes. They noticed that the equations describing a non-rotating black hole could be interpreted as connecting 2 separate regions of space-time through a narrow geometric bridge. This structure, later named the Einstein-Rosen bridge, was the first mathematical description of what would eventually be called a wormhole. But the Einstein-Rosen bridge was not a useful shortcut. It pinched off too quickly for anything, even light, to pass through. It existed as a transient geometric feature that formed and collapsed faster than any signal could traverse it. For decades, it remained a mathematical curiosity with no physical significance. That changed in the mid-1980s, when Kip Thorne at the California Institute of Technology received a peculiar request. The astronomer and author Carl Sagan was writing a science fiction novel called Contact, and wanted a scientifically plausible method for his characters to travel across the galaxy. Sagan had originally used a black hole, but Thorne pointed out that falling into a black hole is a one-way trip ending in destruction, not a viable transport mechanism. Thorne suggested an alternative, a traversable wormhole, a stable geometric tunnel through space-time connecting 2 distant regions. Then Thorne did something remarkable. Instead of leaving the idea as fiction, he assigned the problem to his graduate student Michael Morris, and together they published a rigorous analysis in the American Journal of Physics. The Morris-Thorne paper of 1988 asked a straightforward question: what would the laws of physics require for a stable, traversable wormhole to exist? They did not start with a physical mechanism and work forward. They started with the desired geometry, a tunnel connecting two distant points through a shortcut in spacetime, and worked backward through Einstein's field equations to determine what kind of matter and energy would be needed to hold it open. The answer was troubling and illuminating in equal measure. A traversable wormhole requires matter with negative energy density threading the throat of the tunnel. Without this exotic material, the wormhole collapses. The throat pinches shut, the shortcut ceases to exist. The gravitational tendency of normal matter is to compress the tunnel, and only matter with gravitationally repulsive properties, matter that violates the weak energy condition, can counteract that compression and keep the passage open. This was the first clear, rigorous demonstration that exotic spacetime shortcuts and negative energy density are intimately linked. The connection would prove to be one of the most important structural insights in theoretical physics. It was not specific to wormholes. It reflected something deep about the relationship between spacetime geometry and the matter that sources it. Geometries that bend spacetime in ways that create shortcuts, bypasses, or effective superluminal transport tend to require matter with properties that violate the energy conditions. This pattern, first identified in the wormhole context, would reappear with devastating consistency in every subsequent proposal for faster-than-light travel. But Thorne's investigation produced an even more disturbing result. In 1988, shortly after the Morris-Thorne paper, Thorne and two collaborators, Morris and Ulva Yurtsever, published a follow-up showing that if traversable wormholes exist, they can be converted into time machines. The logic was elegant and alarming. Take one mouth of the wormhole and accelerate it to high velocity, then bring it back. Special relativistic time dilation means the accelerated mouth has experienced less time than the stationary mouth. The two mouths are connected through the wormhole, so an observer entering the stationary mouth exits from the accelerated mouth at an earlier time. The wormhole has become a gateway to the past, closed time-like curves, time travel, paradoxes. This realization sent shockwaves through the theoretical physics community. It meant that the question of whether traversable wormholes can exist was not merely a question about exotic matter or energy conditions. It was a question about whether the laws of physics permit time travel. Stephen Hawking responded with his chronology protection conjecture, proposing that quantum effects would always intervene to prevent the formation of closed time-like curves, effectively forbidding traversable wormholes, warp drives, and any other mechanism that could enable faster-than-light signaling. The conjecture was never proven, but it crystallized the stakes of the debate. Research into exotic spacetime geometries was no longer a niche pursuit. It was probing the deepest structural constraints of physical law. The wormhole research program of the late 1980s and early 1990s established the conceptual vocabulary, the mathematical tools, and the key physical constraints that would define the warp drive field for the next 3 decades. It identified the central role of the energy conditions. It revealed the connection between spacetime shortcuts and exotic matter. It raised the spectre of causality violations. It developed the analytical methods for evaluating whether a proposed geometry is physically admissible. And it demonstrated that general relativity, the same framework whose predictions have been confirmed from solar eclipses to colliding black holes, permits spacetime geometries that look like science fiction while demanding matter that looks like science impossibility. When Miguel Alcubierre sat down in 1993 to think about whether Star Trek's warp drive could be described in the language of general relativity, he was not working in a vacuum. He was entering a conversation that Thorne, Morris, and their collaborators had already been having for half a decade. The tools were ready, the questions were framed, the energy conditions were understood, the causality concerns were on the table. Alcubierre's contribution was to show that the same class of exotic spacetime geometry that produced traversable wormholes could also produce something different. Not a tunnel through spacetime, but a wave of spacetime. Not a shortcut between two fixed points, but a moving bubble that carries its contents forward at any desired speed. The problems were the same: exotic matter, energy condition violations, causality paradoxes. But the geometry was new, and the new geometry opened new questions that the wormhole framework alone could not answer. Miguel Alcubierre was not trying to change physics. He was trying to settle a bar argument. The year was 1993. He was 29 years old, a doctoral student in numerical relativity at Cardiff University, studying the mathematical machinery of Einstein's field equations. His Friday nights followed a comfortable pattern. He and his friends gathered to watch Star Trek, The Next Generation. They drank, they talked, and occasionally the physicist in him would collide with the science fiction on screen. One evening, after watching the Enterprise leap to warp speed, someone asked whether anything like that could actually work. Alcubierre started thinking about it in the shower the next morning. He expected the answer to be a clean, definitive no. Within weeks, he realized the answer was something far more disturbing. What Alcubierre discovered was a specific solution to the Einstein field equations that described a region of flat spacetime, completely undistorted, enclosed within a shell of carefully curved geometry. The curvature had a particular structure. Directly ahead of the flat region, spacetime contracted. Directly behind it, spacetime expanded. The net effect was a wave of geometry that moved through the universe, carrying the flat interior along with it. A spacecraft sitting inside the flat region would experience no acceleration, no time dilation, no sensation of movement at all. It would simply rest in place while the spacetime around it flowed like a conveyor belt, sweeping it forward at any desired velocity, including velocities greater than the speed of light. The mathematics was not complicated by the standards of general relativity. Alcubierre described the geometry using a modified version of the standard ADM formalism, a way of slicing spacetime into spatial layers evolving through time. He introduced a function that controlled the shape of the warp region and a velocity parameter that set the speed of the bubble. The resulting metric was clean, well-defined, and free of the kind of coordinate singularities that plague many exotic spacetime geometries. Inside the bubble, space was perfectly flat. Outside the bubble, space was perfectly flat. Only in the thin shell between inside and outside did the curvature become extreme, and that thin shell was where all the physics happened. He titled the paper, "The Warp Drive, Hyperfast Travel Within General Relativity." It was published in May of 1994 in Classical and Quantum Gravity. In the paper, Alcubierre was careful to note that his solution was a proof of concept, not a proposal for engineering. He explicitly stated that the geometry required exotic matter with negative energy density, a form of matter that violates the energy conditions normally assumed to hold in nature. He acknowledged that the solution raised serious questions about causality, and he described the result as reminiscent of the warp drive of science fiction, while stopping short of claiming it could ever be built. The physics community responded with a mixture of fascination and alarm. Here was a solution to Einstein's equations, published in a top journal, describing faster-than-light transport without any local violation of the speed limit. The mathematics checked out. The geometry was self-consistent. The solution belonged to the same theoretical framework that predicts black holes, gravitational waves, and the expansion of the universe. It was not fringe science. It was general relativity doing something nobody had asked it to do. But the problems were immediate and severe. The first and most devastating was the energy requirement. To produce the kind of spacetime curvature Alcubierre's bubble demanded, you would need a specific distribution of energy throughout the warp shell, and that energy had to be negative, not zero. Not merely small, profoundly, enormously negative. Negative energy density means matter, or fields whose gravitational effect is repulsive rather than attractive. It means material that weighs in effect less than nothing. Ordinary matter always has positive energy density. Even antimatter has positive energy. Negative energy density is something qualitatively different, something that belongs to the fringes of theoretical physics rather than the shelves of any laboratory. In 1997, Physicists Michael Fenning and Larry Ford at Tufts University subjected the Alcubierre metric to a rigorous energy analysis. Their results were staggering. For a warp bubble roughly 100 meters across, traveling at 10 times the speed of light, the total negative energy required was staggering. Depending on the bubble size and velocity, estimates range from quantities comparable to the total mass energy of the observable universe to quantities exceeding it by many orders of magnitude. The total mass energy of the observable universe, every star, every galaxy, every particle of dark matter, every photon of background radiation, adds up to roughly 10 to the 53rd kilograms. Early analyses of the Alcubierre metric demanded negative mass energy concentrations that dwarf this figure entirely. Alcubierre's warp drive for a single small spacecraft would not merely consume a significant fraction of the energy content of everything that exists. It would require more negative energy than the positive energy contained in the observable universe. Every star, every galaxy, every particle of matter in the entire visible cosmos converted to energy would not supply enough to run this drive for a single trip, and the problems compounded from there. Fenning and Ford also showed that the negative energy had to be confined to an extraordinarily thin region. The thickness of the warp bubble wall scaled inversely with velocity. At superluminal speeds, the wall would need to be thinner than a Planck length, roughly 10 to the negative 35th meters, the smallest meaningful distance in physics. Below that scale, spacetime itself is believed to dissolve into quantum foam. The concept of a smooth geometric wall ceases to have meaning. The drive was not just impractical, it required conditions that might not be physically coherent. The causality problem was equally fundamental. Special relativity prohibits faster-than-light travel, in part because superluminal signals would allow paradoxes. If you can send information faster than light in one reference frame, the mathematics of Lorentz transformations guarantees that you can send information backward in time in another reference frame. This means a superluminal warp drive, used in combination with ordinary motion, could in principle create closed time-like curves, paths through spacetime that loop back to their own starting point, a time machine. Most physicists regard the existence of time machines as a reductio ad absurdum, a sign that whatever produced them must be unphysical. The same causality concern that Thorne identified in the wormhole context applied directly to Alcubierre's geometry. If a warp bubble can carry a spacecraft faster than light, the mathematics of Lorentz transformations guarantees that the trip can be arranged to arrive before it departs in some reference frame. Closed time-like curves. Time travel. The chronology protection conjecture that Hawking had already proposed in response to traversable wormholes applied with equal force here. If the conjecture is correct, superluminal warp drives cannot exist regardless of what the classical equations permit. So by the late 1990s, the Alcubierre Warp Drive appeared to be a beautiful mathematical curiosity trapped behind three impassable barriers: impossible energy requirements, unphysical matter properties, and causality violations. Most physicists expected the concept to fade into obscurity. It did not. Instead, a steady stream of researchers began chipping away at the barriers, not to prove the drive was feasible, but to understand exactly where the boundaries of possibility lie. Harold White, then working at NASA's Johnson Space Center, was among the first to make significant progress. In 2011, White published an analysis showing that reshaping the bubble from a sphere into a torus, a donut-like ring of warped spacetime, and optimizing its thickness could reduce the energy requirement by orders of magnitude, from universe scale to something closer to the mass energy of a large planet. Still far beyond any conceivable technology, but the number had moved from infinity to merely impossibility, and in theoretical physics, that distinction matters. White went further. He proposed laboratory experiments using a modified Michelson interferometer to detect microscopic spacetime distortions that might indicate warp-like effects. The experiments were conducted at NASA's Eagle Works laboratory. The results were inconclusive and drew significant skepticism from the broader physics community. But the effort itself was notable. A NASA facility was spending time and resources investigating warp drive physics. The idea had moved from the theoretical fringe to the institutional periphery. Meanwhile, other researchers explored alternative warp geometries. Jose Notario proposed a variant in 2002 that achieved the transport effect without expansion and contraction of space, using a different arrangement of the shift vector. His version still required negative energy. Chris van den Broek found a way to dramatically reduce the total energy by shrinking the bubble's cross-section while maintaining a large internal volume, essentially making it bigger on the inside than the outside. Each modification taught physicists something new about possible warp spacetimes, even as the core barriers remained. Then came 2021, and the field experienced what felt like a phase transition. 3 independent groups published results that seemed to attack the exotic matter problem directly. The first was Alexei Bobrik and Gianni Martir, working through the research organization Applied Physics. Their paper, titled Introducing Physical Warp Drives, appeared in Classical and Quantum Gravity in April of 2021. It did not propose a specific new warp drive. It did something more fundamental. It created a general mathematical framework that encompassed all possible warp drive spacetimes, including configurations that no one had previously considered. Their central insight was deceptively simple but profound. Any warp drive, including the Alcubierre drive, is fundamentally a shell of material, regular or exotic, moving inertially through spacetime. The warp effect comes from the particular arrangement of matter in the shell and the curvature it generates. This framing allowed Bobrik and Martir to classify warp spacetimes into categories based on their physical properties. Some categories required exotic matter, others did not. Some were superluminal, others were subluminal. Some violated energy conditions, some satisfied them. The headline result was that a specific class of subluminal, spherically symmetric warp drives could in principle be constructed using only positive energy. No exotic matter required. These drives would not exceed the speed of light, but they would produce a genuine warp effect, passengers carried by the curvature of space-time rather than pushed through it by a conventional engine. No acceleration forces, no time dilation relative to the external universe beyond what ordinary velocity produces. A smooth ride through warped geometry using nothing but regular matter. But Bobrik and Martir were also careful to state what their framework could not do. Superluminal warp drives, in their classification, still required some form of exotic energy. And any warp drive, even a subluminal one, required propulsion. The bubble does not spontaneously accelerate. Something has to push the shell of matter to its desired velocity before the warp effect engages. The warp drive is not a magic engine. It is a configuration of spacetime that offers unusual transport properties, but it still has to be set in motion by external means. They also optimized the Alcubierre metric itself, showing that modifications to the bubble shape could reduce the negative energy requirement by 2 orders of magnitude. Not enough to make the superluminal version feasible, but enough to demonstrate that the original energy estimates were not fundamental limits. They were consequences of specific geometric choices. The second major paper came from Eric Lentz, then a postdoctoral researcher at the University of Göttingen. Lentz published Breaking the Warp Barrier in Classical and Quantum Gravity in March of 2021, and the claim was extraordinary. He proposed a new class of spacetime solitons, self-sustaining wave-like structures that could travel at superluminal speeds while being sourced entirely by positive energy densities. If correct, this would have demolished the single biggest barrier to faster-than-light travel. No exotic matter, no negative energy, superluminal speed, using only the kind of energy that exists in nature. Lentz's approach was mathematically distinct from both Alcubierre and Bobrik-Martir. Instead of working with the standard warp bubble geometry, he constructed soliton solutions in Einstein-Maxwell plasma theory, a version of general relativity coupled to electromagnetic fields and plasma. He identified specific configurations where the shift vector could support superluminal motion while the energy density, as measured by co-moving Eulerian observers, remained non-negative everywhere. The energy requirements were still enormous, roughly equivalent to the mass energy of hundreds of Jupiters for a 100-meter spacecraft at light speed. But the energy was positive, conventional. The kind of energy released by nuclear reactions and matter-antimatter annihilation. Impractical in the extreme, but not unphysical. The paper generated enormous public attention. News outlets around the world reported that a scientist had found a way to make warp drives work with real physics. The coverage was, predictably, far more enthusiastic than the paper warranted. But even within the physics community, the result drew significant interest. If Lentz was right, the theoretical landscape had fundamentally changed. A third group contributed to the wave. Fell and Heisenberg published their own positive energy warp drive geometries in classical and quantum gravity in July of 2021, using what they called hidden geometric structures to construct spacetimes with non-negative energy densities. Their approach was different from both Bobrick-Martier and Lentz, adding another independent line of evidence that positive energy warp configurations might exist. Within the span of a few months, 3 separate research groups had published in the same premier journal, all pointing toward the same conclusion. Warp drives might not require exotic matter after all. The old assumption that negative energy was an inescapable feature of all warp spacetimes appeared to be crumbling. For a brief moment, the theoretical barrier that had stood for 27 years seemed to be falling. The energy requirements were still absurd, the engineering was non-existent, and no one had any idea how to actually build any of these configurations. But the principle seemed to have shifted. The question was no longer whether warp-like spacetimes could exist without exotic matter. The question was how far they could be pushed. Could the positive energy approach be extended to superluminal speeds? Could the energy requirements be reduced to something even remotely practical? Could the geometry be refined into something an engineer might one day recognize as a blueprint? The excitement was real, the publications were real, the mathematics was real, and then a team of physicists published a response that brought the celebration to a sharp and uncomfortable halt. Jessica Santiago, Sebastian Schuster, and Matt Visser were already among the most respected voices in the subfield of exotic spacetime geometries. Visser, in particular, had spent decades studying wormholes, energy conditions, and the mathematical subtleties of general relativity. He literally wrote the textbook on Lorentzian wormholes. When their response appeared, first as an arXiv preprint in May of 2021, and then in Physical Review D in March of 2022, the community paid attention. Their argument was precise and devastating. The 3 recent papers claiming positive energy warp drives had all checked the energy conditions using a single class of observers. The co-moving Eulerian observers, the observers riding along with the bubble. For these observers, the energy density appeared positive, but the weak energy condition does not ask whether one particular observer sees positive energy. It asks whether all time-like observers see positive energy. Every possible observer moving at every possible velocity through the warp region must measure non-negative energy density. If even one observer, in one reference frame, at one point in the spacetime, measures negative energy density, the condition is violated. Santiago, Schuster, and Visser showed that when you perform this more careful analysis, when you check the energy conditions for all observers rather than just the most convenient ones, generic warp drives violate the null energy condition. The situation was, in their precise phrasing, much grimmer than advertised. The positive energy claims were not wrong in a trivial sense. They had correctly calculated the energy density seen by Eulerian observers, but they had not demonstrated what they claimed to demonstrate. Satisfying the energy condition for one class of observers is not the same as satisfying it for all observers, and the distinction is not academic. It is the difference between a physical solution and a mathematical artifact. This did not entirely invalidate the earlier work. the Bobrick-Martier framework remained a valuable classification tool. The subluminal positive energy warp drives they described might survive the more stringent analysis depending on their specific geometry. The Fuchs et al. Paper that would appear in 2024 was specifically designed to satisfy all energy conditions, not just the Eulerian ones, which is why it represents a genuine advance. But the superluminal positive energy claims, the ones that had generated the most excitement, were now under severe pressure. The pattern had reasserted itself. Breakthrough, then limitation, hope, then constraint. The wall cracks, and then the crack fills in, except it never fills in completely. The subluminal results survived, the computational tools remained, the classification framework endured. Each cycle of excitement and correction left the field slightly more advanced than before, with a slightly clearer map of what is permitted and what is forbidden. And that pattern was about to repeat itself again, because the limitations went deeper than energy conditions. The obstacles facing any warp drive concept, even a theoretically perfect one, extend into quantum mechanics, information theory, and the fundamental structure of cause and effect. The wall was about to fight back harder than anyone expected. The critique from Santiago, Schuster, and Visser did not kill warp drive research. It did something more subtle and, in the long run, more important. It forced the field to confront a question that had been lingering since Alcubierre's original paper. What does it actually take for a warp spacetime to be physically real, rather than merely mathematically consistent? Because in general relativity, those are two very different things. Einstein's field equations are extraordinarily permissive. You can write down almost any space-time geometry, plug it into the equations, and they will tell you what distribution of matter and energy is required to produce it. This reverse engineering approach is how most exotic geometries are discovered. Alcubierre started with the curvature he wanted and asked the equations what kind of energy would create it. The equations answered honestly. The answer was negative energy density, distributed in a precise and unphysical pattern. This reverse engineering trick works for wormholes, warp drives, time machines, and all manner of geometries that appear in the theoretical literature. The equations do not object. They produce solutions for anything you feed them. The constraint on what is physically real comes not from the equations themselves, but from the energy conditions. A set of restrictions on the stress-energy tensor that codify our best understanding of what real matter and energy can do. The energy conditions are not derived from first principles. This is a point that gets lost in popular discussions, and it matters enormously for the warp drive story. The weak energy condition states that the energy density measured by any time-like observer must be non-negative. The null energy condition states that the quantity measured along any null geodesic, any path followed by a light ray, must be non-negative. The dominant energy condition requires that the flow of energy never exceeds the speed of light. The strong energy condition, the most restrictive, demands that gravity is always attractive in a specific technical sense. These conditions were formulated in the 1960s as assumptions that seemed physically reasonable, supported by every known form of classical matter. They are not theorems, they are constraints imposed by physicists based on experience, not consequences proven from deeper laws. This distinction is critical because quantum field theory, the framework governing particle physics and the behavior of matter at the smallest scales, already violates some energy conditions in limited contexts. The Casimir effect is the most famous example. When two uncharged metallic plates are placed extremely close together in a vacuum, quantum fluctuations of the electromagnetic field create a measurable attractive force between them. The energy density of the vacuum between the plates is negative relative to the vacuum outside. This is confirmed experimentally. It is real, and it violates the weak energy condition. Hawking radiation provides another example. Stephen Hawking showed in 1974 that black holes emit thermal radiation due to quantum effects near the event horizon. This process requires the creation of negative energy flux that falls into the black hole while positive energy escapes as radiation. The energy conditions are violated in the vicinity of the horizon. The violation is tiny, but it is physical, and it is essential to one of the most important results in modern theoretical physics. These quantum violations are real but severely constrained. Larry Ford and Thomas Roman showed in the 1990s that quantum mechanics imposes its own restrictions on how much negative energy can exist, where it can exist, and for how long. These restrictions are called quantum inequalities, and they function as a second layer of defense against exotic spacetime geometries. Even if the classical energy conditions can be violated by quantum effects, those violations are bounded. You cannot accumulate unlimited negative energy in a region. The magnitude of the negative energy density is inversely related to the duration and spatial extent over which it persists. Large negative energy densities can exist only for extremely short times in extremely small volumes. The more negative energy you try to concentrate, the more aggressively quantum mechanics pushes back. The mechanism behind this constraint is worth understanding because it reveals something fundamental about how the universe manages its energy budget. Quantum mechanics does not simply forbid negative energy, it permits it, but imposes a strict and mathematically precise system of accounting. Whenever negative energy appears in a region of space, the laws of quantum field theory require that positive energy must also appear nearby, and the positive surplus must always exceed the negative deficit when averaged over time and space. This is not a vague tendency, it is a quantitative bound. Ford and Roman derived explicit inequalities relating the magnitude of a negative energy pulse to its duration and spatial extent. A pulse of negative energy with density ρ lasting for a time interval delta t must satisfy a relationship in which the product of the energy density and the square of the duration is bounded from above by a fixed constant related to the speed of light and Planck's constant. The more intense the negative energy, the briefer it must be. The more space it occupies, the weaker it must become. Think of it as a loan from the quantum vacuum. You can borrow negative energy, but the universe charges interest. The larger the loan, the faster you must repay it, and the repayment, a compensating surge of positive energy, always exceeds the original debt. Small loans are easy. The Casimir effect borrows a tiny amount of negative energy between closely spaced metal plates, and the quantum vacuum collects its positive surplus from the surrounding region without difficulty. The transaction is microscopic, fleeting, and self-balancing. But a macroscopic loan, the kind needed to sustain a warp bubble wall across a region meters or kilometers wide for any useful duration, would require repayment on a scale that dwarfs the original negative energy. The bookkeeping becomes catastrophic. The positive energy surplus needed to compensate for a macroscopic region of sustained negative energy would itself require concentrations of energy beyond anything known in nature. This quantum bookkeeping explains why the Casimir effect exists, but a warp drive does not. The universe permits local, temporary, microscopic violations of the energy conditions because the accounting works out at those scales. It does not permit large, sustained macroscopic violations because the accounting cannot balance. Every attempt to scale up the Casimir-like effects runs headlong into constraints that grow more punishing with every order of magnitude. The universe is not saying negative energy cannot exist. It is saying negative energy is expensive, and the price rises faster than any conceivable budget can cover. For the Alcubierre Warp Drive, the quantum inequalities are ruinous. The drive requires enormous negative energy densities sustained indefinitely over macroscopic distances. The quantum effects that produce negative energy in the Casimir effect generate quantities roughly 40 orders of magnitude, too small and confined to regions billions of times, too narrow to sustain a macroscopic warp bubble wall. The gap between what quantum mechanics permits and what the warp drive requires is not a technical challenge to be solved with better engineering. It is a chasm so vast that no known physics offers even a conceptual bridge across it. But here is where the story resists the clean ending that debunkers prefer. The quantum inequalities were derived within specific theoretical frameworks, primarily quantum field theory on flat or mildly curved backgrounds. Whether they apply unchanged in regions of extreme spacetime curvature, like the wall of a warp bubble, remains an open question. Some researchers argue that the inequalities should hold everywhere because they arise from fundamental properties of quantum fields. Others suggest that the interplay between quantum mechanics and strong gravitational fields might produce surprises. We do not have a complete theory of quantum gravity, the framework that would unify general relativity with quantum mechanics. Until we do, any statement about what quantum effects permit or forbid in strongly curved spacetime carries an asterisk. The asterisk is small, but it is there. The Lentz superluminal claim faced an even more specific reckoning. In late 2025, physicist Bill Selmaster published a detailed analysis examining Lentz's warp drive geometry directly. Selmaster did not simply repeat the general argument from Santiago, Schuster, and Visser. He performed a direct calculation of the energy-momentum tensor for Lentz's specific soliton solution, working in the Eulerian reference frame. The very frame in which Lentz had claimed the energy density was everywhere non-negative. Selmaster found that the energy density was negative in specific spacetime regions. The claim of positive energy was incorrect even for the class of observers Lentz had selected. But Selmaster went further. He examined the theoretical derivations in Lentz's original paper and identified several mathematical errors. Specific equations and inequalities that Lentz had used to establish his positive energy criteria contained mistakes. When those mistakes were corrected, the criteria themselves changed, and the corrected criteria were not satisfied by the soliton geometry Lentz had proposed. Selmaster then constructed a modified version of Lentz's geometry, one that more closely respected the corrected equations and inequalities. Even this improved version still violated the weak energy condition, producing regions of negative Eulerian energy density. This result was significant because it distinguished the Lentz claim from the broader subluminal results. The Bobrick-Martyr framework and the later Fuchs et al. Paper had been careful to limit their positive energy claims to subluminal configurations. Lentz had made the much stronger claim of superluminal positive energy travel. That stronger claim now appeared to be based on derivation errors, and when those errors were corrected, the result reversed. Superluminal warp drives, powered by positive energy alone, remained undemonstrated. The community working on warp spacetime classification reinforced this conclusion from a different angle. A comprehensive analysis paper that appeared in early 2026 systematically reviewed the claims made by Bobrick and Martyr, Fuchs and colleagues, Lentz, and several other groups working on related problems. The authors argued that many correct critiques from Santiago et al. Had been ignored in subsequent papers by proponents of physical warp drives. The analysis was blunt. The field had developed a pattern of successive papers building on foundations that had already been shown to be compromised, without adequately addressing the criticisms. This is an uncomfortable dynamic in science, but not an unfamiliar one. When a result generates excitement, subsequent work tends to build on it rather than interrogate it. Citations accumulate. New papers reference the original without rechecking its foundations. A body of literature develops that appears to support a conclusion, but rests on assumptions that were challenged early and never fully defended. The warp drive literature is not unique in this regard, but the stakes of the claim, faster than light travel, make the pattern particularly consequential. Beyond the energy conditions, the warp drive faces a problem that is less mathematical and more conceptual, but potentially just as fatal. It is called the horizon problem, and it strikes at the question of control. Consider a superluminal warp bubble in operation. The spacecraft sits inside a region of flat spacetime, carried along by the curved geometry of the bubble wall. The pilot wants to steer, to slow down, to change direction, or to stop. To do any of these things, the pilot needs to send a signal from the interior of the bubble to the bubble wall, because the wall is where the curvature lives, and the curvature is what produces the motion. But the bubble is moving faster than light. Signals from the interior travel at the speed of light. They cannot catch up to the leading edge of the bubble. The front wall is receding from the interior faster than any signal can propagate. The pilot has no causal contact with the part of the warp field that controls the drive's direction and velocity. This means a superluminal warp drive cannot be controlled from inside. The pilot cannot turn it on, turn it off, accelerate, decelerate, or steer. And then, all of those operations require causal influence on the bubble wall, and causality travels at the speed of light. At superluminal speeds, the geometry itself creates an event horizon between the occupant and the control surface. The drive would need to be activated and configured entirely from outside the bubble, by some external agent who arranges the matter and energy in advance along the entire trajectory. The spacecraft would be a passenger on a pre-built track, not a vehicle under its own power. It is worth pausing to absorb what this actually means for anyone inside the bubble, because the experience would be unlike anything in human history. Imagine boarding this spacecraft. The warp field activates. From your perspective, nothing changes. The interior of the bubble is flat space-time. Gravity feels normal. Clocks tick normally. You can pour a glass of water without distortion. Through a viewport, starlight ahead would be drastically blue-shifted, compressed into a brilliant ring, while the rearward sky stretches into deep infrared darkness. But you feel nothing. No acceleration. No vibration. No sensation of speed. You are stationary within your pocket of flat space. The space itself is moving, and you have no control over any of it. You cannot throttle the engine because there is no engine inside the bubble. The mechanism that produces your motion is the curvature of the bubble wall, and the bubble wall is causally disconnected from you. You cannot send a radio signal to it, you cannot throw a switch that affects it. You cannot fire retro thrusters to slow down because your thrusters operate within the flat interior, and the flat interior is not what is moving. You are not flying, you are being carried. The difference between a pilot and a passenger has never been more absolute. At subluminal speeds, this problem is manageable because signals from the interior can still reach the bubble wall. Causal contact is maintained, but the moment the bubble exceeds light speed, the forward wall recedes faster than any signal you send. You are sealed inside. The warp drive becomes a sealed envelope moving through the cosmos at a velocity you did not choose, on a trajectory you cannot alter, toward a destination you cannot change. You will arrive when the geometry delivers you, or you will not arrive at all, and there is nothing you can do about either outcome. This is not a minor engineering difficulty. It strikes at the conceptual heart of what it means to travel. A vehicle that cannot be controlled by its occupants is not transportation. It is ballistic trajectory. It is a bullet. The superluminal warp drive, even if it could be powered, would reduce its passengers to cargo, conscious cargo, sealed inside a geometric structure that moves by the arrangement of exotic matter laid down in advance by someone else somewhere else at some earlier time. The romance of warp travel, the captain issuing commands, the navigator adjusting course, evaporates entirely. What remains is a deeply strange form of conveyance that requires an entire infrastructure of pre-positioned exotic matter, built by conventional means at conventional speeds before the first passenger ever steps aboard. Some researchers have proposed workarounds. Perhaps the bubble geometry could be pre-configured so that it follows a desired trajectory without requiring real-time input. Perhaps an advanced civilization could lay down a corridor of carefully arranged exotic matter in advance, creating a kind of warp highway that spacecraft traverse passively. These proposals are not obviously impossible, but they transform the warp drive from a vehicle into an infrastructure project of literally cosmic proportions. Building the highway requires placing exotic matter along the entire route before the first trip. This reintroduces the same energy and matter problems the drive was supposed to solve. The causality issue returns here with renewed force. If a superluminal warp drive exists, and if it can be used to travel between 2 points faster than light in one reference frame, then the mathematics of special relativity guarantees that there exists another reference frame in which the trip occurs backward in time. The arrival happens before the departure. This is not a matter of perception or measurement convention. It is a direct consequence of the Lorentz transformations that relate different inertial frames. Two such trips, arranged appropriately, would allow sending information into one's own past. Closed time-like curves, time travel paradoxes. The grandfather paradox is made physically real. Most physicists regard this as a sign that superluminal travel in any form is forbidden by a principle deeper than the energy conditions. Hawking's chronology protection conjecture formalizes this intuition, asserting that nature enforces a blanket prohibition on any geometry that would permit travel into the past. If this conjecture is correct, then no arrangement of matter and energy, however mathematically elegant, can produce faster-than-light transport because the universe will not tolerate the time travel paradoxes that would follow. The warp drive would be forbidden not because the equations reject it, but because the universe enforces a deeper consistency requirement that the classical equations do not capture. But the chronology protection conjecture is precisely that. A conjecture. It has not been proven. Hawking himself acknowledged that a proof would likely require a complete theory of quantum gravity, which does not yet exist. The conjecture is well motivated. It is supported by several partial results in semi-classical gravity, but it is not a theorem, and treating it as one would be scientifically premature. This brings us back to the Fuchs et al. Paper from 2024, the result that motivated the recent headlines. It is worth examining this paper more carefully because it represents the most rigorous positive energy warp result to date, and because understanding exactly what it achieves and what it does not reveals the true state of the ROM field. Fuchs and his team did not simply write down a metric and calculate its energy content. They built their solution numerically, using a computational toolkit called Warp Factory that the Applied Physics Group developed specifically for evaluating warp drive spacetimes. The toolkit solves Einstein's field equations for a given warp geometry, calculates the full stress-energy tensor, and evaluates all four classical energy conditions at every point in the spacetime and for all observer frames. This is the key methodological advance. Previous positive energy claims had checked the conditions for Eulerian observers only. Fuchs used numerical methods to check them for all time-like observers, addressing the Santiago-Schuster-Visser critique directly. The resulting solution combines a stable matter shell, a thick layer of extremely dense positive energy material, with a shift vector distribution that closely matches the Alcubierre metric. The shift vector is the mathematical component that produces the warp effect, the sliding of spatial coordinates that sweeps the interior forward through the surrounding geometry. Inside the shell, the shift vector creates a genuine warp bubble. Outside the shell, space-time is ordinary. The shell itself satisfies all energy conditions. No negative energy anywhere, for any observer. But the solution is explicitly subluminal. The shift vector produces a warp effect, but the bubble does not exceed the speed of light. Fuchs was candid about this limitation. He stated clearly that the result is not going to solve the Star Trek-like future of rapid transport. The speed of the bubble is slower than light, meaning the drive cannot reach other star systems any faster than a conventional spacecraft traveling at the same velocity. What the drive does offer is unique. It accelerates passengers without any g-forces using regular matter. The occupants experience no acceleration, no inertial effects, no forces at all. They are carried by geometry rather than pushed by thrust. This is physically interesting and potentially useful for certain applications, but it is not faster than light travel. The distinction matters enormously, and it gets lost in almost every popular discussion of this result. A subluminal warp drive is a fascinating object of theoretical physics. It demonstrates that warp-like effects can exist within known physics. It shows that the connection between exotic matter and warp drives is not absolute. It provides a proof of concept that space-time can be engineered to carry passengers in ways that conventional propulsion cannot replicate. But it does not break the speed of light. It does not bypass the cosmic speed limit. It does not enable interstellar travel on human timescales. The word subluminal is doing all the heavy lifting in that paper, and it is the word that disappears from every headline. The energy requirements, even for the subluminal version, remain extraordinarily large. The shell of matter must be unimaginably dense, concentrated into a configuration that no known material or technology could produce. The total mass of the shell, for a bubble large enough to enclose a spacecraft, would approach or exceed planetary masses. Moving that shell to the desired velocity before engaging the warp effect requires propulsion on a scale that dwarfs any conceivable engine. The solution is physical in the sense that it does not violate known laws. It is not physical in the sense that anyone could build it. This is a distinction that runs through the entire warp drive literature and causes persistent confusion. When physicists say a solution is physical, they mean it does not require matter or energy with properties that contradict known physics. They do not mean it is practical, achievable, or anywhere near technological feasibility. A sphere of neutron degenerate matter, the mass of Jupiter shaped into a precise toroidal configuration and accelerated to a significant fraction of the speed of light, is physical in the sense that it does not require exotic matter. It is not physical in the sense that anyone will ever make one. The gap between does not violate known laws and can actually be done is measured in orders of magnitude so vast that the distinction approaches the gap between mathematics and engineering fiction. The pattern of the last 30 years now comes into focus with uncomfortable clarity. Alcubierre found a valid superluminal warp geometry, but it required impossible energy and exotic matter. White reduced the energy requirements by orders of magnitude, but the exotic matter remained. Bobrick and Martier showed that subluminal warp drives could work without exotic matter, but the superluminal version still required it. Lentz claimed to have found superluminal positive energy solitons, but the claim was challenged and then shown to contain errors. Fuchs demonstrated a rigorous positive energy warp solution satisfying all energy conditions, but it was subluminal. White redesigned the warp bubble into a modular nacelle architecture, but it still required negative energy for superluminal operation. Each result advanced the field. Each result taught physicists something new about the landscape of warp spacetimes. Each result was published in a serious journal after serious peer review, and each result left the most important barrier standing. Superluminal travel using only positive energy has not been demonstrated. Every configuration that breaks the speed of light also breaks the energy conditions. Every configuration that satisfies the energy conditions stays below the speed of light. The correlation is not accidental. Multiple independent theoretical results suggest it reflects a deep structural feature of general relativity and quantum field theory. Kenneth Olam proved in a 1998 paper that superluminal travel in general relativity necessarily requires violations of the weak energy condition under very general assumptions. The Santiago-Schuster-Visser result reinforced this for generic warp geometries. The quantum inequalities constrain how much negative energy quantum effects can provide. Together, these results paint a picture of a universe that permits extraordinary geometric tricks at subluminal speeds, but erects increasingly formidable barriers as you approach and try to cross the speed of light. Yet the barriers are not proven to be absolute. They depend on energy conditions that are assumptions rather than theorems. They depend on quantum inequalities derived in specific frameworks. They depend on semi-classical approximations that may break down in strongly curved regions. They depend on the chronology protection conjecture that remains unproven. Every barrier carries a caveat. Every impossible comes with a footnote. The question is whether those footnotes matter, whether the caveats represent genuine openings in the physics or merely the inevitable uncertainty of any scientific claim, whether the fact that we cannot prove faster than light travel is forbidden is the same as saying it might be possible. These are not purely technical questions. They sit at the boundary where physics meets epistemology, where the structure of our theories meets the limits of what we can know. And they are the questions that keep serious researchers coming back to a problem that should have been closed decades ago. The answer to why the field survives, why papers keep appearing, why top journals keep publishing them, lies not in the results themselves, but in what the results reveal about the deepest theory of spacetime we possess. General relativity permits geometries that look like they should carry objects faster than light. It does so without contradiction, without singularity, without any internal inconsistency. The inconsistency appears only when you ask what kind of matter is needed to produce those geometries, and the answer violates conditions that we believe hold in nature but cannot prove hold in nature. The entire prohibition rests on the space between belief and proof, and that space, narrow as it is, turns out to be wide enough for a research program. There is a question that haunts every physicist who has ever spent serious time thinking about warp drives. It is not whether faster than light travel is possible. That question, for all its drama, has a relatively straightforward provisional answer. Almost certainly not, given everything we currently know. The question that actually haunts them is different. It is quieter. It sits in the background of every calculation, every paper, every conference talk. And it is this: why does the mathematics keep letting them ask? General relativity is not a generous theory. It does not hand out valid solutions lightly. The Einstein field equations are 10-coupled nonlinear partial differential equations that constrain the geometry of spacetime with extraordinary precision. Finding a solution that satisfies these equations, that is self-consistent, that does not produce singularities or pathologies outside of well-understood limits, is genuinely difficult. Most proposed spacetime geometries fail. They produce contradictions, or they collapse into trivial cases, or they require boundary conditions that cannot be satisfied. The equations are ruthless filters. And yet, when you ask them whether spacetime can be shaped into a geometry that looks like faster-than-light transport, they do not say no. They say yes, but here is what you need to build it. And what you need to build it is a form of matter that may not exist. The refusal is conditional, not absolute. The equations do not reject the geometry. They accept it, and then present a bill that nature may not be willing to pay. This is a profoundly unusual situation in physics. Compare it to other apparently impossible proposals. Perpetual motion machines violate the laws of thermodynamics, and the equations reject them completely. No valid solution describes a machine producing unlimited energy from nothing. The mathematics itself forbids the concept. Similarly, accelerating a massive object to exactly the speed of light produces a genuine divergence in the equations of special relativity, a mathematical infinity that cannot be circumvented by cleverness. The prohibition is absolute, structural, and embedded at the deepest level. Faster than light warp travel is not like that. The mathematics does not reject it. The mathematics produces valid, self-consistent solutions. The rejection comes from a layer above the mathematics. The energy conditions, the quantum inequalities, the chronology protection conjecture. These are physical constraints imposed on the mathematical solutions based on what we believe about the behavior of real matter. They are well-motivated beliefs. They are supported by extensive observation. But they are not proven to be universal laws in the way that energy conservation or the structure of Lorentz symmetry are proven. This distinction matters because the history of physics contains several examples where well-motivated beliefs about what nature permits turned out to be wrong or incomplete. For most of the 19th century, physicists believed that energy was a continuous quantity, that a system could gain or lose energy in arbitrarily small amounts. This belief was so deeply embedded in classical physics that it was rarely even stated as an assumption. Then Max Planck showed in 1900 that the spectrum of thermal radiation could only be explained if energy came in discrete packets, quanta, of a size proportional to frequency. The assumption of continuity was not wrong in the sense of being contradicted by everyday experience. It was wrong in the sense of being an approximation that broke down in regimes where quantum effects become dominant. Similarly, the energy conditions are not wrong in the sense of being contradicted by everyday experience. Every form of matter we can observe in laboratories satisfies them. Every macroscopic energy source we have ever measured obeys them. They are excellent descriptions of the behavior of known matter. The question is whether they are exact descriptions of the behavior of all possible matter, including matter in extreme gravitational environments, at Planck scale densities, or in configurations that have no analogue in our current experience. As we have already seen, quantum field theory produces genuine violations of the classical energy conditions. The Casimir effect, Hawking radiation, and squeezed vacuum states in quantum optics all demonstrate that negative energy densities can occur in nature. These violations are experimentally confirmed. They are also, as we explored, severely constrained by quantum inequalities that prevent any macroscopic accumulation of negative energy. The universe's bookkeeping appears ruthlessly precise, but the violations exist, and their existence proves a principle that matters enormously for the warp drive question. The classical energy conditions are not inviolable laws derived from first principles. They are well-motivated constraints that hold for every known form of macroscopic matter but break down in specific quantum regimes. The distinction between a law and a well-motivated constraint is the distinction between a locked door and a door that has been closed but never tested. Whether the quantum breakdowns can ever be amplified or sustained in ways that would enable a warp drive remains an entirely separate question, and the answer from current physics is almost certainly no. The constraints grow more restrictive as the violation grows larger. No known mechanism bridges the gap between the microscopic violations that quantum mechanics permits and the macroscopic violations that a warp drive demands. But the word known carries weight. The constraints were derived within specific theoretical frameworks. Whether they survive unchanged into the domain of quantum gravity, where spacetime itself becomes a quantum object, is precisely the question that no one can yet answer. The deeper issue is that all of these analyses are performed within the framework of quantum field theory on curved but classical spacetime backgrounds. This is a semi-classical approximation. It treats the geometry of spacetime as a smooth classical object governed by general relativity, while treating the matter fields living on that geometry as quantum objects governed by quantum field theory. This hybrid framework has been spectacularly successful. It predicts Hawking radiation, the Casimir effect, inflationary cosmology, and the generation of primordial density fluctuations that seeded cosmic structure. But it is known to be incomplete. It breaks down in regimes where the curvature of spacetime itself is so extreme that quantum effects on the geometry become important. At the Planck scale, roughly 10 to the negative 35th meters and 10 to the negative 43 seconds, spacetime itself is expected to become a quantum object, subject to fluctuations, superpositions, and entanglement. What happens to the energy conditions in that regime is unknown, because we do not have a complete theory of quantum gravity. This is not a hypothetical concern. The wall of a superluminal warp bubble, if one could exist, would involve curvature approaching Planck scale intensity. The Fenning-Ford analysis showed that the bubble wall would need to be thinner than a Planck length. At those scales, the semi-classical approximation breaks down entirely. Statements about what quantum field theory permits or forbids in that regime are extrapolations from a framework that is known to be invalid there. They might be correct, they might not. We cannot currently tell. The phrase, "we do not have a complete theory of quantum gravity," passes by quickly, but it represents the single deepest unsolved problem in all of fundamental physics, and the warp drive question sits squarely in the territory it leaves uncharted. To understand why the absence of quantum gravity matters so profoundly here, you need to understand what it means that our two best theories of nature are fundamentally incompatible. General relativity describes gravity as the curvature of smooth, continuous spacetime. In this framework, spacetime is a fabric that can stretch, compress, ripple, and warp, but it is always smooth. You can zoom in as far as you like and the geometry remains well-defined, continuous, differentiable. Quantum mechanics describes everything else in the universe, particles, forces, fields, as fundamentally discrete and probabilistic. Energy comes in packets. Measurements produce inherently uncertain outcomes. Fields fluctuate even in the vacuum. When you zoom in on matter far enough, the smooth classical description dissolves into a fizzing sea of quantum uncertainty. For most purposes, these two frameworks operate in separate domains. General relativity governs the very large, stars, galaxies, the expansion of the universe. Quantum mechanics governs the very small, atoms, particles, subatomic interactions. They rarely need to talk to each other. But in extreme environments where enormous mass is concentrated into tiny volumes, the two theories collide. The center of a black hole, where all the mass is compressed to a single point. The first instant of the Big Bang, where the entire observable universe was smaller than a proton, and the wall of a superluminal warp bubble, where space-time curvature reaches Planck-scale intensity across a region thinner than any meaningful length. In these regimes, you need both theories simultaneously. You need quantum mechanics because the scales are microscopic. You need general relativity because the curvatures are extreme. And when you try to combine them, when you try to apply quantum rules to the smooth space-time fabric of general relativity, the mathematics produces catastrophic infinities. The calculations blow up, predictions become nonsensical. The framework that works beautifully for particles on flat space-time and the framework that works beautifully for smooth curvature on large scales simply refuse to merge into a single coherent description. This is not for lack of trying. The greatest theoretical physicists of the last century have attacked this problem. Candidate approaches exist. String theory proposes that the fundamental constituents of nature are tiny vibrating filaments of energy requiring 10 or 11 dimensions to vibrate consistently, with smooth spacetime emerging as an approximation that breaks down at the Planck scale. Loop quantum gravity takes a different approach, proposing that space itself is quantized into discrete loops of gravitational field, forming a granular structure that only appears smooth from a distance, the way a sheet of fabric reveals individual threads under a microscope. Other approaches, including causal set theory, asymptotic safety, and emergent gravity, offer still different visions of what spacetime looks like at its most fundamental level. None of these candidates is complete. None has been experimentally confirmed. None currently provides a definitive answer to the question that matters for this story. What happens to the energy conditions when space-time curvature reaches Planck scale intensity? Do the classical energy conditions survive intact into the quantum regime? Do they soften? Do they transform into something different? Do entirely new constraints appear that are more restrictive or less restrictive than the classical ones? We do not know. And until someone completes a theory of quantum gravity and derives the answer from first principles, every statement about what is and is not permitted at the wall of a superluminal warp bubble carries a fundamental and irreducible uncertainty. The prohibition on faster-than-light travel may be absolute, but the proof of that prohibition requires a theory that does not yet exist. This is the crack in the wall. Not a proof that faster-than-light travel is possible, not a blueprint for a starship, not even a plausible path toward engineering. It is something far more subtle and far more unsettling. It is the recognition that the prohibition against faster-than-light travel, which feels absolute and ironclad in popular discussion, actually depends on assumptions that have not been proven in the regimes where they matter most. The equations of general relativity permit the geometry. The energy conditions forbid the matter. The energy conditions are well motivated, but not proven. The quantum corrections are real, but not fully understood. And the regime where everything matters most is precisely the regime where our best theories admit they do not apply. This is why the field survives. This is why credible scientists continue to publish. They are not chasing science fiction. They are probing the boundary between what our theories allow and what nature enforces. Every new warp paper is, at its core, a test of that boundary. Does this particular geometry require exotic matter? Does this particular configuration violate the energy conditions for all observers or just some? Can this particular arrangement of positive energy matter produce a warp effect? Each answer narrows the landscape. Each result tells us something new about the structure of spacetime and the constraints on how it can be shaped. The most recent contributions continue this narrowing process. Harold White's 2025 nacelle paper did not solve the exotic energy problem, but it demonstrated that the architecture of warp bubbles is far more flexible than the original Alcubierre design suggested. By distributing the warping energy into discrete cylindrical structures rather than a continuous toroidal ring, White showed that the geometry can be adapted to configurations that look more like engineering designs and less like abstract mathematics. The nacelles create regions where the most intense curvature is confined to specific zones, keeping the inhabited interior flat and stable. The paper confirmed that these configurations are fully consistent with general relativity and that key parameters like interior flatness and nacelle spacing are tunable. This does not bring faster-than-light travel closer to reality in any practical sense, but it expands the theoretical design space in ways that might matter if the exotic energy problem is ever resolved. At the other end of the spectrum, the Santos Pereira group at the Federal University of Rio de Janeiro has been pursuing a different approach entirely, studying what happens when you use ordinary fluid matter as the gravitational source for warp metrics instead of the standard vacuum or negative energy sources. Their doctoral thesis, published in 2025, presented new solutions for the Einstein field equations applied to the Alcubierre spacetime, demonstrating that fluid source models can produce warp-like effects under certain conditions. They also developed methods for matching the Alcubierre spacetime with the flat Minkowski spacetime of our everyday universe, addressing the technical question of how a warp bubble would connect to the surrounding cosmos. These results do not overcome the fundamental barriers, but they demonstrate that the theoretical territory is larger and richer than many physicists assumed. The computational infrastructure of the field has matured significantly. The Warp Factory toolkit developed by the Applied Physics Group represents a qualitative advance in methodology. Previous warp drive research relied heavily on analytical calculations, which favor simple metric forms that can be solved by hand. Warp Factory allows numerical evaluation of arbitrary warp geometries, computing the full stress energy tensor, evaluating energy conditions for all observer frames, and generating visualizations of the curvature distribution. This capability enables researchers to explore vast families of warp spacetimes that would be inaccessible to analytical methods. It transforms warp drive research from a boutique theoretical exercise into something closer to a systematic survey of possibilities. The field has also developed a classification system, thanks largely to the Bobrick-Martier framework. Warp spacetimes are now categorized into classes based on their velocity regime, energy properties, and geometric structure. This classification reveals that the Alcubierre metric, the geometry that started everything, is just one point in a vast parameter space of possible warp configurations. Most of those configurations have never been studied. Some might have properties that differ significantly from the Alcubierre case. The classification does not promise that a physically admissible superluminal warp drive exists somewhere in that parameter space, but it demonstrates that the question has not been exhaustively answered. The territory is too large and too poorly explored for definitive negative conclusions. The research agenda going forward reflects this unfinished cartography. Several groups are working to map the energy condition landscape across broader families of warp metrics, systematically identifying which geometries satisfy which conditions and under what constraints. The Applied Physics Group has stated that their next priority is reducing the mass energy requirements of subluminal physical warp drives, searching for configurations where the dense matter shell becomes less extreme, potentially bringing the concept closer to something that future generations of physicists might recognize as a distant engineering target, rather than a pure mathematical abstraction. Other researchers are pursuing the interface between warp geometry and quantum field theory, calculating the semi-classical back reaction of quantum fields on warp spacetimes to determine whether quantum effects stabilize or destabilize these configurations. This line of work connects warp drive research directly to the broader effort to understand quantum fields in curved spacetime, one of the most active areas of theoretical physics. On the experimental side, ambitions remain modest but real. White's group at Casimir has discussed developing laboratory analogues, tabletop experiments using metamaterials or electromagnetic configurations designed to mimic certain geometric features of warp spacetimes without actually curving spacetime. These experiments cannot produce a warp bubble, but they could validate computational models and provide empirical benchmarks for the theoretical predictions. Meanwhile, the Warp Factory toolkit continues to be refined and expanded, with its developers releasing it as a publicly available tool accessible to any researcher who wants to evaluate new warp geometries. The democratization of the computational infrastructure means that the next significant result could come from any university, any research group, any physicist with a new idea and the mathematical skills to test it. The field is no longer dependent on a handful of specialists. It has developed the tools, the frameworks, and the institutional credibility to sustain a genuine, if small, research community working at the intersection of general relativity, quantum field theory, and the outer boundaries of what spacetime permits. None of this should be mistaken for progress toward a working faster-than-light drive. It should not be mistaken for evidence that such a drive is possible. It should not be mistaken for a reason to expect interstellar travel within any foreseeable future. The barriers remain standing. The exotic energy problem is unsolved. The quantum inequalities are formidable. 10, 10, 10. The causality concerns are profound. The engineering gap between a mathematical solution and a physical device spans so many orders of magnitude that it defies meaningful comparison. But the honest assessment is also not a simple dismissal. The honest assessment is uncomfortable, ambiguous, and unresolved. It is that general relativity, the most successful theory of gravity and spacetime ever developed, permits geometries that describe faster-than-light transport. It is that the prohibition on those geometries comes from auxiliary assumptions that are well supported but not proven. It is that quantum mechanics already violates those assumptions in limited regimes. It is that the regime where the assumptions matter most is the regime where our theories break down. It is that trained physicists at established institutions continue to produce new results, subject them to rigorous peer review, and develop increasingly sophisticated tools to explore the question. And it is that no one, not the optimists and not the skeptics, can currently prove their position from first principles. The warp drive question is, at its deepest level, a question about the completeness of our understanding of spacetime. If general relativity and quantum field theory together provide a complete description of the constraints on spacetime geometry, then faster-than-light warp drives are almost certainly impossible. The energy conditions and quantum inequalities leave no room. But if our understanding is incomplete, if quantum gravity modifies the energy conditions in ways we cannot currently predict, if the Planck scale physics of the bubble wall permits effects that semi-classical analysis misses, then the situation is genuinely open. Not open in the sense of being likely, open in the sense of being unresolved by the evidence currently available. The history of physics offers no reliable guide here. Sometimes, well-motivated prohibitions turn out to be absolute. The impossibility of perpetual motion has survived every challenge for over a century. Sometimes, well-motivated prohibitions turn out to be conditional. The impossibility of transmitting information without a physical carrier was absolute, until quantum entanglement revealed that correlations can exist between distant particles. Though the no-communication theorem preserves the speed of light limit for usable information, the lesson is not that all prohibitions eventually fall. The lesson is that the status of a prohibition depends on the depth and completeness of the theory from which it derives. Prohibitions rooted in exact theorems of complete theories are reliable. Prohibitions rooted in assumptions within incomplete theories carry uncertainty. The faster-than-light prohibition falls into the second category. This is why the title of this story asks a question rather than making a claim. Have scientists found a real way to travel faster than light? No. They have not. The subluminal results are real but do not break the speed limit. The superluminal claims have been challenged and in key cases refuted. The exotic energy barrier stands for every configuration that exceeds the speed of light. No experimental evidence of any kind supports the existence of a mechanism for faster-than-light travel. But have scientists found that the prohibition is less absolute than it appears? Yes, they have. The geometry is permitted by the equations. The energy conditions are assumptions, not theorems. The quantum violations are real, even if constrained. The theory breaks down in the regime that matters most. The parameter space of warp geometries is vast and largely unexplored. The computational tools to explore it are improving. The results keep coming. The real shock is not that anyone solved faster-than-light travel. No one did. The real shock is that the deepest theory of space-time we possess still refuses to close the door. Not because the door is open. Not because anyone can walk through it, but because the lock depends on mechanisms we do not fully understand, and the key might exist in a part of physics we have not yet discovered. Every few years a new paper appears. The headlines announce a breakthrough. The skeptics explain why it is not. The optimists explain why it might be. The truth sits in between, narrow and uncomfortable. The warp drive remains exactly what it has been for 30 years. A theoretically permitted geometry that cannot be realized with any known form of matter or energy, studied by serious scientists who keep finding that the reasons it cannot work are not quite as ironclad as they should be. There is something deeply strange about living in a universe whose fundamental laws permit the geometry of faster-than-light travel, while apparently forbidding the matter needed to achieve it. It is as if the universe drew a blueprint for a machine, and then hid all the materials. The blueprint is real. The equations confirm it. The architecture has been refined, optimized, redesigned, and classified into families. But the materials remain missing, possibly non-existent, possibly hiding in a corner of physics we have not yet explored. Maybe the materials do not exist. Maybe the energy conditions are exact. The quantum inequalities are universal, and the chronology protection conjecture is correct. Maybe general relativity permits these geometries as mathematical curiosities with no physical significance, artifacts of a classical theory that a future quantum theory of gravity will eliminate. Maybe faster-than-light travel is exactly as impossible as it seems, and the theoretical cracks are illusions created by the incompleteness of our current framework. Or maybe the cracks are real, maybe the energy conditions are approximations, maybe quantum gravity opens doors that semi-classical physics keeps closed. Maybe the universe is stranger than the current generation of theories can describe, and the warp drive question is probing exactly the boundary where known physics ends and unknown physics begins. We do not know. We cannot currently know. The question remains open not because the evidence favors faster-than-light travel, but because the evidence against it, overwhelming as it appears, rests on foundations that have not been proven in the regimes where they are most needed. The line between impossible and merely unattainable is supposed to be clean. In this case, it is not. It is blurred, contested, and tangled in the deepest unresolved questions in fundamental physics. The relationship between gravity and quantum mechanics, the nature of space-time at the smallest scales, the ultimate constraints on what matter and energy can do. Somewhere tonight, a physicist is running a new metric through the Warp Factory toolkit, checking energy conditions, looking for configurations no one has tried. Somewhere else, a graduate student is reading the Alcubierre paper for the first time and feeling the same jolt that Alcubierre felt when the equations refused to say no. They are not building a starship. They know that. But they are doing something that matters. They are testing the walls. They are asking whether the verdict that the cosmos handed down, the verdict that says every civilization is alone, sealed behind distances that light itself takes lifetimes to cross, is truly final. And they keep finding that the walls while standing are not quite as solid as everyone assumed. Scientists have not found a way to travel faster than light, but they have found that space-time itself, the deepest structure of reality, leaves just enough ambiguity, just enough unexplored territory, just enough theoretical tension for the question to remain alive. Not as science fiction, not as wishful thinking, as a genuine, unresolved problem at the frontier of physics. And that might be the most unsettling answer of all. Not yes, not no, not yet.